Hello students, welcome to the lecture Differentiation and Integration, and after this lecture we will be able to learn the following objectives. Define derivative. Explain the derivatives of sum and difference. Understand the product and quotients. Discuss the chain rule, derivatives of composite functions. Explain the antiderivatives. Describe the integration by substitution. Understand the integration by parts. Let's start with the concept of differentiation and integration. Differentiation is a method to compute the rate at which a dependent output y changes with respect to the change in the independent input x. This rate of change is called derivative of y with respect to x. In more precise language, the dependence of y upon x means that y is a function of x. This functional relationship is often denoted y equals to f of x, where f denotes the function. If x and y are real numbers and if the graph of y is plotted against x, the derivative measures the slope of this graph at each point. The simplest case is when y is a linear function of x, meaning that the graph of y against x is a straight line. In this case, y equals to f of x, which is equal to mx plus b for real numbers m and b, and the slope m is given by as shown here. Where the symbol delta, the uppercase form of the Greek letter delta, is an abbreviation for change in. This formula is true. This gives an exact value for the slope of a straight line. If the function f is not linear, that is, its graph is not a straight line, however, then the change in y divided by the change in x varies. Differentiation is a method to find an exact value for this rate of change at any given value of x. The rate of change as a limiting value. Integration was first introduced as the reverse of differentiation. A more rigorous treatment would show that integration is a process of adding or summation. By viewing integration from this perspective, it is possible to apply the techniques of integration to finding areas, volumes, centers of gravity, and many other important quantities. A thorough understanding of the process involved is essential if we need to apply integration techniques to practical problems. Integration is the inverse operation of differentiation and is a measure of the area under a curve. Area below the x-axis counts as negative. Another technique for calculating some integrals whose results are not obvious is a kind of inverse product rule and is called integration by parts. Where u and v are functions of x, as an example of this, let's do the integral of x sine x dx. Another type of substitution is trig or hyperbolic substitution. Suppose that we have the integral as shown here. If we make the substitution x equals to sine theta and dx equals to cos theta and d theta, then the integral becomes as shown on the screen.
People with even a nodding acquaintance with calculus take it as a given that differentiation and integration are the opposites of each other. This, in fact, is the crux of the first fundamental theorem of calculus. According to this, if you take a function, integrate it, and then differentiate the result, then you'll get back the original function. Why should this be so? Every calculus book has a proof, but let's leave the mathematical rigor aside and understand it intuitively. The integral of a function is the area under the curve of the function. Given that this is so, and that the derivative is the rate of change of a function, we are seeking the rate at which the area under the curve changes with respect to changes in x. To see this, let us consider a point B to the right of A and see how much this changes the area by. When x increased from A to B, that is by B minus A, the area under the curve increased by the area of the shaded region, whose height is approximately f of A and width is B minus A. I say the height is approximately f of A because the height is in fact not constant and is different at B than at A. However, if A and B are very, very close together, then we can assume that the shaded region is in fact a rectangle with height f of A and width B minus A. The increase in area is therefore f of A times B minus A for a change in x of B minus A. The rate of change of area with respect to x is thus f of a times b minus a divided by b minus a, which is nothing but f of a, the original function's value. That's all there is to it. So we were seeking to find the rate at which the area changes with respect to changes in x. And we found that this was nothing but the value of the function. Another simple way to look at it is, when we increase x by a little bit, a small sliver is added to the area whose width is very small and whose height is the value of the function itself. Thus, the rate at which the area changes with x is nothing but the height, which is the value of the function f.
Let us now discuss about derivative. We shall need to find the value approached by delta y by delta dx as dx tends to 0 in many different situations. There is a special notation used to signify the process, the limit notation. Let y equals to f of x so that delta y equals to f of x plus delta x minus f of x. Then the value approached by delta y or delta x when delta x tends to 0 is denoted by as shown here. The following notations are standard short ways in indicating a derivative: derivative, slope, and tangent. Let y equals to f of x and delta y equals to f of x plus delta x minus f of x. Then the derivative of y respect to x is signified by, as shown on the screen, dy of d or dx should be regarded as a single shorthand symbol representing the longer expression limit delta y or delta x where delta x tends to 0 and not as a ratio which can be taken to pieces. However, its great usefulness is that it often behaves just like an ordinary ratio of non-zero quantities, the rates of change. The quantity limit delta y or delta x where delta x tends to 0 is usually needed to solve problems which have no immediate connection with the slope of the graphs. This idea was only introduced to give the reader a picture to hold on to. Moreover, it is not always appropriate to call the variables x and y if other letters arise naturally.
So, what is a derivative anyway? Derivatives are functions that describe how quickly other functions change. If a function around some value of x moves up in value quickly as the values of x grow, then it could be said that the derivative of this function is large and positive around those values of x. If a function stays about the same as x grows around some neighborhood of x values, then it could be said that the derivative of this function stays close to 0 around those values of x. If for some neighborhood of x values the function decreases in value as x grows, then the derivative of such a function is negative in that neighborhood of x values. You might be concerned that in a neighborhood of x, the function doesn't just go up or down, but it has hills and valleys of all sorts. To keep things simple, we will only consider functions such that if we choose a narrow enough neighborhood of x, then the values of the function only go up or down. The neighborhood that we will consider will be so very tiny that within the function itself, it will lose almost all of its curviness and become almost completely a straight line. If we take a look at the neighborhood of the function f of x at some value x, the size of the neighborhood will be delta x in width. You may notice that as long as we keep our distances very small, it is true that if you increase the size of delta x, the size of delta f of x also increases proportionally. For this reason, we can't simply talk about the size of delta f of x, but we must consider the proportion of the size of delta f of x to the size of delta x. This is another way of saying that we are interested in the ratio delta f of x over delta x, which is also called the rate of change. We could consider all kinds of other relationships between these two values, such as delta x over delta f of x, or arctan delta f of x over delta x, or some other relationship, but the most useful measure of the slope in the later applications of calculus happens to be delta f of x over delta x. If we make the two numbers infinitesimally small, then all that we are left with is the exact rate of change at that particular position, which is going to be called the derivative. And the function that provides the value of the derivative at the position of x is written f prime of x. How do we know that the ratio doesn't just disappear and become zero or infinity as the delta x and delta f of x are shrunk? This has to do with something called limits that our more formal calculus book covers in greater detail, but for us it is sufficient to imagine that the two sides of a triangle describing the rate of change have the same proportions to each other regardless of how small the triangle itself becomes. Therefore, if f of x has a derivative, then f prime of x is equal to delta f of x over delta x, where delta f of x and delta x are infinitesimally small at each particular value of x.
Now moving on to we will study the derivatives of sum and the difference. The following are general rules which become obvious when the definition is applied to them. The derivatives of some linear combination of functions. If c is constant, then look at the screen for the derivatives. The derivatives of difference, linear combination of functions. If c is constant, then. Let's now know the meaning of product and quotients. The product rule and the quotient rule are used to differentiate products of functions and quotients of functions. The product rule. It is appropriate to use this rule when we wanted to differentiate two functions which are multiplied together. For example, y equals to ex is sine x, product of the function ex and sine x. In the rule which follows, we let u stand for the first of the function and v stand for the second. The quotient rule. It is appropriate to use this rule when we want to differentiate a quotient of two functions, that is, one function divided by another. For example, y equals to ex or sine x is a quotient of the function ex and sine x. In the rule which follows, we let u stand for the function in the numerator and v stand for the function in the denominator. Chain rule, derivatives of composite functions. The composition rule is usually called the chain rule, but the word composition has more direct meaning in this context. When we recognize that the function we want the derivative of is a composition, then naturally it makes sense to use the composition rule. Just like recognizing that a function is a product tells us that we should use the product rule. We will first do an example using the chain rule directly. Then we will develop another table that will be much more convenient to use. We can do this because there are only 5 functions that can be used in the composition. However, we can of course have more than one composition in a problem. We then handle this as before, one step at a time. If we do not know what it means by one step at a time, then we should review on the decomposing a function into its elementary pieces. Look at the screen for an example. That is how it works in general. Now we will give a table with all possible compositions. We should be aware of the fact that we might have to use the table more than once in a particular problem, as well as one or more of the previous rules. All of these formulas are derived from the general chain rule, with f of x one of the elementary functions, xn, ex, 1nx, sin x, cos x, and an arbitrary function g of x. Now we will do some examples, especially the first step, that is showing that you know which formula to use and how to use it without computing the derivatives of the component functions until after the first step. On the test, the various kinds of problems will be mixed together, so the first thing to be done is to determine if we have a constant times a function, the sum of functions, product, quotient, composition, or piecewise functions for the first step. What we are doing in the following examples is to first determine that we have a composition of functions. This is the function algebra stuff. This means that we should use one of the above formulas. Identify which of the above formulas we should use: power, exponential, log, sine, or cosine rule. Determine what the g of x is and then plug in. Do not skip the first step. This is not so easy to determine in general. So now is the time to practice thinking about it.
Hey everybody, in this video I'm going to show you how to take the derivative using the chain rule. So let's just get started right away with an example. Let's say we have the function f of x is equal to 3x squared plus 5. Let's say it's all raised to the 10th power. And the first thing I want to talk to you about is when do you need to use the chain rule. And anytime you see a parentheses followed by an exponent, that is your dead giveaway that you have to use the chain rule. So it's really important that you remember that anytime you see a parentheses followed by an exponent, you have to use the chain rule. And the cool thing about using the chain rule is that it allows us to take the derivative of this function without expanding. Obviously, if we expanded something to the 10th power, that would take forever. So it saves us a lot of time, and it's very useful. So let's just get started right away with this example. If we have the function f of x is equal to 3x squared plus 5 to the 10th power, the derivative, and before I take the derivative, I'm just going to copy and paste just to save a little bit of time. So I wrote for you all the steps for taking the derivative on the left-hand side. And the first step for taking a derivative using the chain rule is we want to bring the exponent to the front. It's the same as the power rule. So we want to take this exponent of 10 and we want to bring it to the front and multiply it. The inside of the parentheses stays exactly the same, so I'm going to keep my 3x squared plus 5. And our third step is we want to subtract the exponent by 1. So since there was a 10 exponent in our original function, 10 minus 1 is 9, there's going to be a 9 exponent in our derivative. And then moving on to our last step is we want to multiply everything by the derivative of the inside of the parentheses. Okay, notice inside the parentheses there's a 3x squared plus 5. So the derivative of the inside, the derivative of 3x squared is just 6x. And the derivative of positive 5 is just 0. So the derivative of 3x squared plus 5 is just 6x. And we want to multiply that. So now we have taken the derivative using the chain rule, and we always need to simplify this as much as possible. And the only way this can be simplified is this 10 can be multiplied by the 6x. So if you multiply the 10 by the 6x, that gives you a 60x. And the parentheses stay the same. And we can't forget about our 9 exponent. Now we have taken a derivative using the chain rule.
Antiderivatives. Recall that we say big F is an antiderivative of a small f if big F equals to small f. Here are some examples. Notice that we go up from the bottom row to the top by carrying out a differentiation. To go down, we must undo that differentiation. The process of reversing or undoing a differentiation has come to be called an differentiation. You should differentiate each function on the bottom row to check that it is an antiderivative of the function above it. While a function can have only one derivative, it has many antiderivatives. For example, cos u and 99 minus cos u are also antiderivatives of the function sin u. In fact, every function c cos u is an antiderivative of sin u for any constant c whatsoever. This observation is true in general. That is, if f is an antiderivative of a function f, then so is f plus c for any constant c. This follows from the addition rule for derivatives. It is tempting to claim the converse, that every antiderivative of f is equal to big F plus c for some appropriately chosen value of c. In fact, we will often see this statement written. The statement is true, though only for continuous functions. If the function f has breaks in its domain, then there will be a more antiderivatives than those of the form f plus c for a single constant c over each piece of the domain of small f. Big F can be modified by a different constant and still yield an antiderivative for small f. If small f is continuous, though, big F plus c will cover all the possibilities, and we sometimes say that big F plus c are the antiderivatives of small f. For the sake of keeping a compact notation, we will even write this when the domain of small f consists of more than one interval. We should understand, though, that in such cases, over each piece, big F can be modified by a different constant. We collect a list of basic functions whose antiderivatives we already know. Remember that each antiderivative in the table can have an arbitrary constant added to it. All of these antiderivatives are easily verified and could have been derived with at most a little trial and error fiddling to get the right constant, using antiderivatives. According to the fundamental theorem, we can use an indefinite integral to find the value of a definite integral. And this largely explains the importance of antiderivatives. In the language of indefinite integrals, the statement of the fundamental theorem takes the following form. There are clear advantages to using antiderivatives to evaluate definite integrals. We get exact values and we avoid many lengthy calculations. The difficulty is that the method works only if we find a formula for the antiderivative. There are several reasons why we might not find the formula we need. For instance, the antiderivative we want may be a function we have never seen before. The function arc tan x is an example. Even if we have a broad acquaintance with functions, we may still not be able to find the formula for a given antiderivative. The reason is simple. For most functions we can write down, the antiderivatives is just not among the basic functions of calculus. Integration by substitution. We converted a couple of great general rules for differentiation. The rules for the derivative of a constant times a function and the rule for the derivative of the sum of two functions into equivalent rules in integral form. In this chapter, we will develop the integral form of the chain rule and see some of the ways this can be used to find antiderivatives. Suppose we have functions f and g with corresponding derivatives f, small f and small g. F into g of x equals to f into g of x. G of x equals to f into g of x into g of x. If we now take the indefinite integral of these equations, we get as seen here on the screen, where c can be any constant. The integral form reversing these equalities to get a statement about integrals we obtain as seen here on the screen. This somewhat unpromising expression turns out to be surprisingly useful. Here is how. Suppose we want to find an indefinite integral and say in the integrand pair of functions g and g where g dash equals to g and where g of x can be factored out of the integrand. We then find a function f so that the integrand can be written in the form f into g of x into small g of x. Now we only have to find an antiderivative for f. Once we have such an antiderivative, call it big F, then the solution to our original problem will be big F into g of x. Thus, while original antiderivative problem is not yet solved, it has been reduced to a different, simpler antiderivative problem that, when all goes well, will be easier to evaluate. Such reduction methods are typical of many integration techniques. More substitutions. In some cases, rearrangement is needed before the form of an integral becomes apparent. The idea is to reduce each one to the form of an elementary integral whose antiderivative is known. However, finding which of these forms is appropriate in a given case will take some ingenuity and algebra skills. Integration tends to be more of an art than differentiation, and recognition of patterns plays an important role here. Trigonometric substitutions. Trigonometric functions provide a rich set of interconnected functions that show up in many problems. It is useful to remember three very important trigonometric identities that help to simplify many integrals. These are essential trigonometric identities as shown here. In the special case that a equals to b equals to x, the last two identities above lead to double-angled trigonometric identities as shown. The method described here is important as an additional tool for integration. It also has independent theoretical stature in many applications in mathematics and physics. The essential idea is that in some cases we can exchange the task of integrating a function with the job of differentiating it. The idea rests on the product rule for derivatives. Suppose that u of x and v of x are two differentiable functions, then we know that the derivative of their product is as shown here, or in the differential notation as shown here. Now in the end, let us summarize what we have learned in this lecture. The process of finding a derivative is called differentiation. The rate of change is called the derivative of y with respect to x. The derivative of f collects all the derivatives of f at all the points in the f domain of f. Integrals with products or powers of trigonometric functions are simplified by application of trigonometric identities or simple substitution. A vector-valued function, y of t of a real variable, sends real numbers to vectors in some vector space Rn. Substitution is the first method to consider. This method works provided the change of variable results in elimination of the original variables and leads to a simpler, more elementary integral. The integration by parts formula for functions u of x, v of x is as shown here. The area has been found as the limit of a sum and of course agrees with that calculated by integration. A function f is an antiderivative of f if f equals to f. Every antiderivative of f is equal to f plus c for some appropriately chosen constant c.